you want the black one?
Hello, I hope there's a sound going on. Hear me. So let me know if whoever will come, let me know if you can hear me. But at the same time, I can tell that I don't expect anybody to show up because I'm a very small content producer. And in this regards, it's my first live stream, so the less people see my first very embarrassing attempt at that, the better. So in this regards, I want to start by saying that today I want to go over stoichiometry conversions between mass, mole, and number of particles, and mole to mole and mass to mass conversions. Okay, with that in mind, let me start. So the concept of mole plays an important role to connect mass and number of particles. So mass, usually in chemistry we express it in grams, can be converted into moles, and moles can be converted into the number of representative particles. Okay, the type of representative particles. There will be three mostly used particles that we will be talking about. It will be atoms, if we're talking about elements, atoms, or it can be molecules, if we're talking about covalent compounds, or it can be formula units. Okay, so atoms are representative particles of elements. Molecules, representative particles of covalent compounds. And formula units, representative particles of ionic compounds. And mole serves as the connection between mass and number of representative particles. Let's see how it works. Okay, let me clean this one up. Okay. Let's say I have 70 grams of iron. It's a relatively big piece of iron, and it is pure element, so it's made out of atoms. If I want to answer the question, how many number of atoms make up that 70 grams, I would need to convert 70 grams into number of moles, and then convert number of moles into number of atoms. For these conversions, we will use the gram formula mass and number, understanding that mole is a specific number. So for the first conversion, I start with information that I know. 70 grams of iron over 1. And I will multiply it by the conversion factor. This conversion factor I will find on the periodic table. The information that we'll find right here. 1 mole of iron weighs 56 grams according to the periodic table. Okay, so I will place, since I want grams to disappear, I place grams to the bottom, I place moles to the top, and now I'm transfer number of moles 1 to the top and number of grams 56 to the bottom. Okay, so that will get me out of grams of iron into moles of iron when these units are cancelled out. Then my next step number 2, I need to get out of moles of iron into number of atoms. Well, what else do I know? I know that 1 mole of iron made of 6.02 times to the 10 to the power of 23 atoms of iron. So this is my second conversion factor that goes over here. I want moles of iron to be cancelled out. I'm placing that into the denominator, and number of atoms iron I'm placing in the numerator. So 1 mole contains 6.02 times to the 10 to the power of 23 atoms. That's it. This is my entire conversion. Now I will scoop it over a little bit and will show that I take all the numerators and I multiply all the numerators to get the number, and unfortunately I need to fetch my calculator. Okay, so 70 times 6.02. My numerators, product of all my numerators, looks like this. 421.4 times to the 10 to the power of 23 divided, product of all denominators is 56. Then I take this number, divide by 56. Turns out to be 7.525 times to the 10 to the power of 23 atoms. Okay, so let's return for a second. Let's see how we went through it. Grams eliminated at first step. Moles of iron eliminated in the second step. And over here, finally, my final unit is atoms of iron. Okay, so let's play it that way around. Let's say somebody told me that I have 52.7 times to the 10 to the power of 23 atoms of iron. And the question is, how many grams would that sample weigh? How many grams of iron do I have? So this time around, I will travel from the number of atoms. I will convert it into the number of moles. And eventually from moles, I will travel to mass, to grams. Mass will be expressed in grams. Once again, we start with what is given to us. This is the information we're starting with. 52.7 times to the 10 to the power of 23 grams, not grams, atoms of iron over 1. Okay. To get out of number of atoms and into the moles, I need to remember the following, that 1 mole of iron contains that many atoms of iron. So since I want atoms of iron to be disappearing, I'm placing this number to the denominator, 6.02 times to the 10 to the power of 23 atoms of iron, and 1 mole of iron goes into the numerator as my unit. Okay, so this is step number 1. Atoms will be converted into number of moles. Now let's look at the step number 2. That would be us converting moles of iron into grams of iron. So in this regards, we're talking about information that we find in periodic table, that 1 mole of iron weighs 56 grams. Where I got this information? Periodic table. Right here, average atomic mass. This number gives us the information about mass of 1 mole of iron. Okay, so since I want moles of iron to disappear, I'm placing 1 mole of iron to the bottom of this fraction, while 56 grams of iron will be in my numerator. So notice this is multiplication sign. This is multiplication sign. This is why these units will be beautifully canceling themselves out until we finally have the final units of gram of iron. So we turn this into product of all numerators. Let's quickly check what it's going to be. 56 times 52.7 will be 2951.2 times to the 10 to the power of 23 divided by product of denominator 6.02 times to the 10 to the power of 23. Okay, these guys get cancelled out. So eventually we have to do final calculation, which shows that our answer is 490 grams. That would be the mass of that initial amount of atoms that we started with. So if I put on a scale, if this is 52.7 times to the 10 to the power of 23 atoms of iron on a scale, then the scale would show me that the mass of this sample is 490 grams. This is what we just calculated this moment. Okay. We will use the same idea to calculate compounds. Just a second. Picking up a good problem for us to solve. How about this? Just a second, looking for it. Let's say we have 3.5 times to the 10 to the power of 23 molecules of H2O. Our representative particles this time around is molecule. Okay, and we are asked what would be the mass in grams of this sample. Once again, we start with number of representative particles. This time it's molecules, number of molecules. We convert it into number of moles, and then we convert it into the mass expressed in grams. For this conversion, we will be using information that 1 mole of water made of 6.02 times to the 10 to the power of 23 molecules of water. Okay, and for this conversion over here, I'm trying to show it behind while not crossing out my previous calculation. We will be using information that we will be using gram formula mass of water, H2O. Gram formula mass of water is 1 mole of hydrogen times 2 plus 16. So it's 18 grams per mole. What does it give us, this information? This information gives us the second conversion factor, that 1 mole of water, of H2O, weighs 18 grams. This is what that unit means. 18 grams per mole means that 1 mole of water weighs 18 grams. So our conversion factor number 1 is right here. 1 mole of water contains that many molecules, and 1 mole of water weighs 18 grams. So let's move with this information forward. So we start with what we've been given. We've been given 3.5 times to the 10 to the power of 23 molecules over 1 molecules of H2O. Okay, we want molecules to disappear, and this is where we're using this conversion factor that we discovered first. And I need to fix my screen issue. Okay, so number of molecules of water, molecules of water, that number goes to the denominator because I want molecules of water to be cancelled out as a result of my calculation, while 1 mole of water becomes my numerator. I'm using this conversion over here. This is what creates the first step. My first step right here. Okay, step number 2. Get out of moles of water into grams of water. This is where I'm going to use this information. Since molecules of water will cancel out on the first step, this time I'm trying to cancel out moles of water. So I will place moles of water at the bottom and grams, my final unit that I want to have, at the top. And based on this information, what do I know? I know that 1 mole of water weighs 18 grams. So that's it. That's my calculation as it is. Then I multiply all the numerators, and I lost my calculator again. So let me fix it. So we are looking at 3.5 times 18 becomes equals 63 times 10 to the power of 23 over product of all denominators is the number over here. These beautifully get cancelled out, and this is what we got as our resulting mass, 10.4 5 grams of water. This is our winning unit because moles of water got cancelled out. Okay, so in this regards, it's always travel between moles and mass, like returning to our original understanding how we deal with this. We can convert between mass and mole by the use of the gram formula mass of compounds, gram formula mass, GFM, gram formula mass, and we can convert between moles and representative particles by our understanding that 1 mole is 6.02 times to the 10 to the power 23 representative particles. This is our conversion factor for mole to representative particles conversion, and gram formula mass of compounds or elements will be our conversion factor for mass and mole. Let's do one more compound and then move on to mole conversions. Okay, let's see. Okay, this is iron. Quick check. Here's an interesting question. How many atoms make up 1 gram of gold? AU is the symbol of gold. Okay, it means that we are pretty much asked to convert mass, that is expressed in grams, 1 gram of gold. We have to convert it first into mole. We cannot directly jump into number of atoms, and then from mole convert it into the number of atoms. Okay, so we start with what is given to us. 1 gram of gold over 1. This is our initial information that we're working on. We want grams, we want for this conversion from mole to, from mass to mole, we will be using gram formula mass or molar mass of gold. We find it on the periodic table. Our periodic table is here. Gold is right here, and its gram formula mass is its molar mass is 197, I think. So for this gram formula mass or molar mass of gold, according to periodic table, is 197 grams per mole. What does it give us? It gives us the following information, that 1 mole of gold weighs 197 grams. This is our first conversion factor. We want grams of gold to disappear. We want moles of gold to be our remaining unit. So the number for grams goes into the denominator. The number for moles go into the numerator. Okay, that will take care of grams, and now we are in the moles of gold. Now we want to make this second step. For this one, we will use our understanding of 1 mole. 1 mole of gold contains 6.02 times to the 10 to the power of 23 atoms of gold. So we're placing, once again, we want moles of gold disappear, so we're placing them at the bottom. And we're placing number of atoms at the top. We're making this placement because we want moles of gold to be cancelled out, and 1 mole contains that number of atoms, 10 to the power of 23. So altogether, we have the setup. So we'll multiply all the numerators, which product of all numerators for this equation, looking here, will be 6.02 times to the 10 to the power of 23 atoms of gold, divided by, we'll multiply all the denominators, 197, which gives us, let's see, my calculation, 0.02 divided by 197, 0.03 times to the 10 to the power of 23. Well, this is not exactly, it's scientific notation, but not perfect scientific notation. So let's express it in perfect scientific notation. That would be 3 times to the 10 to the power of 21 atoms of gold. That's it. Okay, now going into mole-to-mole conversions for balanced reactions. Okay, let's pick some kind of balanced reaction like calcium chloride reacting with potassium, forming 2 moles of potassium chloride and calcium. Okay, so we can see that 2 moles of potassium form 1 mole of calcium. But let's say that we have not 2, but, I don't know, 18 moles of potassium reacting. Okay, so this information, these coefficients, there's invisible 1 in front of calcium. Okay, they give us the conversion mole for this. If we're given 18 moles of potassium, we'll place it over 1. And then to convert this number of moles into the moles of calcium, we will use the information that is given to us by the coefficients. The coefficients are telling us the following. 2 moles of potassium produce 1 mole of calcium. So since we want moles of potassium to disappear, we will place this part of conversion factor to the bottom. Moles of potassium. That will take care of this unit and it will disappear. We will place this part into the numerator. 1 mole of calcium. And that's it. That's pretty much gives us the answer. Multiply all the numerators, 18, multiply all the denominators, 2, answer 9 moles of calcium. Okay, let's see some more examples of this. Let's look at different reaction. How about this? H2 plus N2 forming NH3 ammonia. So let me quickly balance this. Here it is. Okay, once again, coefficients. There is invisible 1 over here. Let's make it visible. The coefficient 1, coefficient 2 and 3, they give us the ratio for conversions. Okay, we know that 3 moles of hydrogen produce 2 moles of ammonia. Okay, what if instead of 3 moles of hydrogen we have 25 moles of hydrogen reacting with nitrogen? Okay, so to convert that into moles of ammonia, I'm trying to convert from moles to moles, moles of hydrogen into moles of ammonia. I will be using the coefficients. The coefficients are telling me the following story, that 3 moles of hydrogen produce 2 moles of ammonia. This is where I took this information. Okay, so I will be using this conversion factor in my fraction over here. I want moles of hydrogen to be cancelled out, so I will place hydrogen part of my conversion to the bottom. 3 moles of hydrogen and 2 moles of NH3 to the top. So moles of hydrogen will be cancelled out and moles of NH3 will be my winning game over here. So I multiply all the numerators, which turns out to be 50. I multiply all my denominator, product is 3, and 50 divided by 3 will be, let's see, 16.7. And my final unit here is moles of NH3. I just did conversion of mole to mole. So, general idea for mole to mole conversions. We are using coefficients for it. For mole to mole conversion, we're using coefficients. Coefficients. Okay, let's do one more of them and then move to mass conversions. I'm using the same equation. I balance it, and just for our practical, we usually do not write number 1, but for our practical purposes, I want us to have this information here. There is, usually we do not write 1 when it's there, but let's put it out there anyway. So let's talk about, let's say, we know that 1 mole of nitrogen reacts with 3 moles of hydrogen. Okay, so let's say I have 15 moles of nitrogen. And my question is, how many moles of hydrogen do I need to react with that amount of nitrogen? Because clearly I need more hydrogen than I usually do. 1 reacts with 3, so 15 will react with how many moles? So once again, I'm looking at those coefficients. They give me the important information that 1 mole of nitrogen reacts with 3 moles of hydrogen. Just to make it more visible, let's use some color. This is where I got this information. This is where I got this story. Okay, so if this is my conversion factor that will help me, I will place it into my fraction over here. I want moles of nitrogen to disappear, so I will place moles of nitrogen into denominator because I want them to be cancelled out. Moles of nitrogen and 3 moles of hydrogen. So moles of nitrogen will be cancelled out and moles of hydrogen will be my final unit. The answer is 45 moles of hydrogen are required to react with 15 moles of nitrogen. Okay. Now let's talk mass to mass conversions. Let me bring up some convenient, already prepared reactions, so it will be a little bit faster for us. Let's say we're talking about the same equation. Nitrogen reacts with hydrogen, forms ammonia, NH3. And I'm given the following information that I have 100 grams of nitrogen, and I am asked, okay, if this is the amount of reacting nitrogen, how many grams of hydrogen would I need to react with it? And as a result of this reaction, how many grams of NH3 grams, how many grams of ammonia will be released or produced as a result of this reaction? Okay, so for conversions mass to mass, I cannot use coefficients. Before, when we did mole to mole, yes, it works beautifully for moles, but not for grams. We actually need to do 3 steps over here. Our step number 1 will be to take mass that is given to us and convert mass of our given compound of, in this case, will be nitrogen. I would need to convert into the moles of nitrogen. Okay. For this purpose, I will be using gram formula mass of nitrogen, and that will be my conversion factor. Then step number 2 will involve coefficients. This is, I will be doing mole to mole conversion that we just practiced like a couple of minutes ago. I will be converting moles of NH2, which I just calculated in the first step. I will be converting it into the moles of hydrogen. Let's start with hydrogen first. Okay. And then step number 3 will be to take that number of moles of hydrogen that we just found out and convert it into grams. Moles of hydrogen, and I will have to convert it into mass of hydrogen. For this, I will be using gram formula mass of hydrogen. Okay, so those 3 steps will be our guiding point. So let me hold it. Okay. I wonder if I can fold it so it would be a little bit more visible to us what we're doing. And here it goes. Okay. Okay, so we start with what is given to us. Mass, 100 grams of nitrogen. And we can see that our first step is supposed to be converting that into moles of nitrogen. To do that, we will use gram formula mass of nitrogen. I will, oops, don't see much. Gram formula mass of nitrogen will be 14 times 2, which is 28 grams per mole. This is great information that gives us the following conversion factor. 1 mole of nitrogen weighs 28 grams. So with this information, I can do my conversion. I want grams to be gone, so grams of nitrogen go to the bottom, 28. And moles of nitrogen go to be my top unit, 1 mole. Okay, so our step number 1 achieved, checkpoint. We're converting mass of nitrogen into moles of nitrogen. Okay, our next thing will be to use coefficients. For this step, we're using coefficients. So what do we see on the reaction? Reaction says that 1 mole of nitrogen reacts with 3 moles of hydrogen. All right? It means that 1 mole of nitrogen reacts with 3 moles of hydrogen. This is my mole-to-mole conversion factor. Okay, I want moles of nitrogen to disappear. So moles of nitrogen go into denominator. 1 mole of nitrogen goes to denominator. 3 moles of hydrogen go into the numerator. And through that, we achieved step number 2. We just did the conversion. The step number 2 is mole to mole. Moles of nitrogen into the mole of hydrogen. We used coefficients. Okay, for the final conversion, we will use gram formula mass of hydrogen, which is simply 2. It's 1 times 2 equals 2 grams per mole. So if we let it here, gram formula mass of nitrogen tells us that 1 mole of hydrogen weighs 2 grams. Good. That's our third conversion factor. Well, this time around, we're trying to get rid of moles of hydrogen. So we're looking here, taking moles of hydrogen and placing them intentionally into denominator. We want them to be canceled out. 2 grams go to the numerator. That's it. 3 steps accomplished. That's a step number 3. Conversion of the moles of hydrogen into the mass of hydrogen. So in this regards, we just need to multiply all the numerators, multiply all the denominators, and divide one by another. So it will be 100 times 3 times 2, we're talking 600, divided by 28, which gives us 21.4 grams of hydrogen. Why I'm so sure? Because I canceled out the units in the process. First, grams of nitrogen have been canceled out. Then moles of nitrogen were canceled out. And finally, moles of hydrogen were canceled out. So 2 grams of hydrogen was the resulting unit of it. Here is my answer. So with this story in mind, let's think about it this way. Let me rewrite this equation. Plus 3 hydrogens produce 2 ammonia, NH3. We know that 100 grams reacted, and we know that 21.4 grams were required to react with it. And we also, as you might remember, asked to calculate how many grams of ammonia has been produced as a result of it. To be honest, over here, we can be a little sneaky. We can use the law of conservation of mass to calculate the mass of NH3, because mass of all the reactants should add up to the mass of all the products. So over here, we're looking at 121.4 grams. That's it. We could do it as easily as this, or we can do the whole 9 yards. Let's just for the checking ourselves, do the total conversion as we did before. Let's start with 100 grams of nitrogen and do exactly what we've done before. First, convert nitrogen into moles of nitrogen. Moles of nitrogen. And this is grams of nitrogen. We're using gram formula mass. 1 mole of nitrogen weighs 28 grams. This is gram formula mass of nitrogen. This comes from GFM of nitrogen. Then we're using coefficients. This information that 1 mole of nitrogen produces 2 moles of ammonia. We want moles of nitrogen to disappear and 2. So the coefficient 1 comes to the denominator and moles of ammonia will be our numerator. Moles of NH3. We got this from the coefficients. Coefficients. Okay. And the last thing that we want to do, we want to convert that number of moles of ammonia into the grams of ammonia. So mole of NH3, 1 mole of NH3 weighs 17 grams. How do I know that? I know that because I calculated gram formula mass of NH3 and it turned out to be 14 plus 3, it is 17 grams per mole. So this thing came from the entire story of 1 gram of ammonia, 1 mole of ammonia weighs 17 grams. So I multiply all the numerators. I multiply all the denominators. I divide one by another. And guess what? The number that comes out of here turns out to be exactly 121.4 grams of NH3, which supports our idea, the law of conservation of mass, and everything else. So we use this equation and we use these 3-step mass-to-mass conversions. So for first conversion, we use gram formula mass of nitrogen, which turned out to be 28 grams per mole. The coefficients that we see in the reaction, 1 mole of nitrogen produces 2 moles of NH3. This is where we're using coefficients, step number 2. And for step number 3, we're converting grams of ammonia into moles of ammonia with the gram formula mass of ammonia, which is 17. And units get cancelled out in the process. Grams of nitrogen cancelled out in the first step. Moles of nitrogen cancel out in the second step. Moles of NH3 cancel out in the third step. Our final unit will be grams of NH3. Maybe one more example and we're going to be done for today. I think it's enough, but one more example before we leave. Then I would need to figure out how to do it better next time. So we always have to check if our equation that we're working with happen to be 2KCl. Happen to be correctly balanced. 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines. Good, balanced. Let's say we're given information that there is 117 grams of potassium reacting, and we are asked to calculate how many grams of chlorine required for this reaction and how many grams, let's put Z because it does not look like grams, Z, how many grams of potassium chloride produced as a result of this reaction. Once again, 3 steps. Our step number 1 will be mass of potassium into moles of potassium. For this, we will be using gram formula mass of potassium. Okay. Step number 2. Let's say in our first problem, we will be doing it to chlorine. Okay. Like we will be figuring out the number of moles of chlorine. Okay. So we will take moles of potassium and we convert it, mole-to-mole conversion, into the moles of chlorine. This is where we're going to use coefficients. And the final step will be taking moles of chlorine and converting it into the mass, answering this question, this X grams. So we will take moles of chlorine and we convert it into mass, into grams of chlorine. For this, we will be using gram formula mass of chlorine. So we would not be doing it twice. Let's quickly do gram formula mass of potassium can be found in periodic table. It is 39 grams per mole. And Cl2 will be 35 and 35, 70. 70 grams per mole. So we start with what is given to us. We are given mass of potassium element, grams, okay, over 1. Step number 1, I will be using this gram formula mass of potassium. I know that 1 mole of potassium weighs 39 grams. I'm placing grams at the bottom intentionally because it will eliminate this unit. Then I will place my step number 2. I will be using coefficients. What do I see in coefficients between this? I see that 2 moles of potassium react with 1 mole of chlorine. There is invisible coefficient 1 right here. So I want moles of potassium to be canceling out. So I'm placing 2 moles of potassium. I'm referring to this unit, to this coefficient over here. And I'm placing 1 mole of chlorine at the top. This will accomplish step number 2. So we're pretty much done with this and with this. Because moles of potassium will disappear, moles of chlorine will be our remaining unit. And the final step, I will be doing moles of chlorine into grams of chlorine. Well, I have gram formula mass already. So what do I know? I know that 1 mole of chlorine, I'm placing it down here in denominator because I want it to be canceled out, weighs 70 grams of chlorine. So once again, as before, when multiply numerators, when multiply denominators, we end up with mass of the chlorine to be 106.5 grams. Okay, so, and since our equation is so straightforward, so easy one, we have 2 reactants and 1 product, Cl2, 2KCl. Now that we know this information and this information, we probably can make it easy pass on calculations and calculate this mass to be the sum of it, which is 223.5 grams. Law of conservation of mass allows us for some shortcuts along the way. But because I very much into checking our calculations all the time, I will do the calculation one more time just to make sure that I'm correct. So I, as before, start by placing 117 grams of potassium over 1. Okay, then I convert it into from mass of potassium to moles of potassium. 1 mole of potassium weighs 39 grams. Then I will be using coefficients that between this and this over here. So 2 moles of potassium, this is the information that I'm using, produces 2 moles of potassium chloride. Okay, that was step 2, mole to mole conversion. And now I need to convert moles of KCl into grams of KCl. Okay, 1 mole of KCl weighs, well, this one I need to calculate. Okay, gram formula mass of KCl is 39 plus 35 gives us 74 grams per mole. Okay, so 74. And that's it. I multiply, I can cancel this thing out, yeah. But I multiply all the numerators, I multiply all the denominators, and guess what? Our final calculation turns out to be exactly what we expected it to be. So that works. The 3 steps of mass-to-mass conversions. Mass of the compound that was given, mass of which you know, into the moles of that compound. Then use coefficients to convert mole to mole. And the third one, convert the moles of KCl of your new compound into the grams. Okay, that's enough for today. This is definitely more than I thought I would do, longer than I thought I would do it. And I think the milky picture is not very helpful, so I would need to figure out the camera and other arrangements for future live streams. Have a nice day. Bye.